So we're going to start talking about Hamilton cycles. And these are often called Hamilton circuits. These are pretty common to say either. So you can say Hamilton cycle or Hamilton circuit. So what is the definition of this? A Hamilton cycle is a cycle that visits each vertex once and only once. Okay, I think I brought this up once before, but it was hard to catch. Let me point it out again. There is a slight contention that the start and the end vertex are visited twice, and they're like an exception to this rule. But from a structural perspective, this is a little bit, I think, a little over the top. Right? I think this is a perfectly good definition. This is correct. So let's do some examples of things with and without Hamilton cycles. And the book is more liberal with their use of the word circuit, Hamilton circuit, and they use the word circuit is kind of forces the visiting each vertices once and only once, and so it does simplify the definition down a bit. But sorry, I've learned it using the word cycle and cycle structure, so I just usually say it that way. Okay, let's take a look at this example. This one definitely has a Hamilton cycle, or Hamilton circuit, and it's simply this, right? It's this outside hexagon thing. Right, so structurally this is the Hamilton cycle. You can also give it a word, right? So you list the vertices in order in which they're visited. And it's when you write it down like this that sort of contention comes up that you're using the beginning and end vertex more than once. Let's be honest, this is actually, I contend this is a defect of how we write down words or data, that we write start to end. And we have to write this twice to link it together. So if we could write words in circles, like this, right? This word, there is no starting and end vertex. You don't even need the start and end, right? It's all written down once and only once. So, right, this whole visiting each vertex once, I think is pretty clear. So hopefully we're ironing that out. You can also see there's like an arrival and an exit at each vertex, right? So there's like two ways in which you can travel to pick a direction. You can see each vertex has the property that you arrive and leave. So the start vertex just splits that up, right? It's you leave the start, and then you eventually arrive at the start to finish it. Okay, so that's what a Hamilton cycle is. Right? They always look like this. If you just take the Hamilton cycle and extract it off the graph and don't use any other parts of the graph, it's always a circle. Right? And notice some features, right? The subgraph that is traced has degree 2 vertices, right? So it always uses 2 edges. Can't use the same edge because if you go back, then you revisit a vertex. So it's always like a degree 2. It's a subgraph that always has degree 2 vertices. All right, let's look at another one. These grids are kind of fun to work with. Relatively fast to draw. Okay, so this thing does have a Hamilton circuit or a Hamilton cycle. Right, this time I'm going to trace it out using another color. There we go. And you can do your own, see if you can come up with some other ones. I'll write this down as a word. So hopefully everyone's the same order, so it's A, E, I. So just following my route here. L, K, J, F, G, H, D, C, B, A. There we go. So not like a complex example, it's just this one has a Hamilton circuit and I can identify it for you. Alright, let's do one that does not have a Hamilton circuit. And this is where things get, I would say, difficult or challenging. Let me do a smaller grid. This is 4x4. Now this one's 3x3. It turns out the 3x3 grid, this graph, fails to have a Hamilton cycle. Alright, so how do you know? Okay, so as I said, once you extract the Hamilton cycle or circuit off of the graph and write it down as a subgraph, it's always a circle. It's always a degree 2, every vertex always has degree 2. Right, it's arranged like that. Since a Hamilton circuit visits each vertex, you know that these corner vertices have to be visited. In fact, my eye is definitely drawn to any degree 2 vertices. I know my only way in and out. Right, so these corner vertices go like this. I'm kind of using the same marking strategy the book uses in there. Hopefully that's consistent. And so you can see that you have to use these edges that I'm marking, right, if you're going to visit the corners. And so what that forces is it forces this cycle here, this outside cycle. And this outside cycle completely misses the interior vertex. So for that reason, I mean, you could write down all the words, but it's easier just to say verbally like I just did. These corner vertices have to be used, and so you're forced having this sort of external cycle there. Alright, that's the bulk of what you can do. Now the rest is kind of just case by case, figuring things out. But it is not easy when a graph does not have a Hamilton cycle to always explain why it doesn't. There is no theorem like the other theorem we have that has this if and only if, right? You check this condition and that tells you whether or not you have a Hamilton cycle. We're going to have a couple that say, okay, if these conditions are met, then for sure you have one. But if they're not met, then we don't know, right? So we'll go through those theorems shortly. Right. But keep in mind, this one does not have a Hamilton cycle, and this is really just a low-hanging fruit version of what could be done. You'll do this in the homework, play around with these some. You'll find examples that don't have Hamilton circuits, but it's quite tricky to figure out why they don't. Okay, so on the next one, we're going to talk about some sufficient condition theorems that explain when graphs do have a Hamilton circuit. But if we fail those hypotheses, as we'll demonstrate, it doesn't mean that we can say no. All right, so I'll see you all on the next one.